Hello, my name is Joseph Ahern, and I'd like to tell you about the prospects of probing the ice giants Uranus and Neptune by means of ring seismology. We hope these investigations can enlighten future ice giant missions and help address important scientific questions about their interiors. Planetary oscillations can be decomposed into a set of normal modes, each of which oscillates at a frequency that depends on the planet's density profile and whether the restoring force is gravity or pressure. P, F, and G modes are ranked here by decreasing frequency. When gravity is the restoring force, we have a G mode. When it's pressure, we have a P mode. An F mode, or fundamental mode, can be either P or G, and we are primarily concerned with the F modes, which have a radial order n equal to 0. The L equals M modes along the long diagonal here are the ones we most expect to find evidence of at their Lindblad resonance locations. Any even L minus M mode is symmetric about the equator and would generate a Lindblad resonance, which excites density waves, whereas any odd L minus M mode is antisymmetric about the equator and would generate a vertical resonance, which excites bending waves. Normal modes of lower oscillation order M probe deeper into the interior of the planet, whereas the higher M modes are more sensitive to the planet's outer layers. Ring seismology at Saturn, also known as chronoseismology, from the Greek word for Saturn, has been successful. A number of wave features in Saturn's C ring, slightly interior to the main A and B rings, have been identified as effects of planetary normal modes. These plots from Chris Mankiewicz show predicted resonance locations outlined by observed wave features. The normal mode's azimuthal order M, which also corresponds to the number of spiral arms, is the vertical axis, and distance from Saturn's center is the horizontal axis. The left plot shows outer Lindblad resonances, and the right plot shows outer vertical resonances. An important result of the success of chronoseismology is that we now have a better understanding of Saturn's interior, including evidence of a stably stratified layer and of a diffuse core. If we're going to identify resonances with normal modes, it's important that we distinguish them from resonances with satellites. A Lindblad resonance with an exterior moon will propagate outward. Also, because we know where the moons are, we can calculate where their Lindblad resonances fall, and some of them line up nicely with some of the outer rings of Uranus, but none of them line up well with the inner rings, beta, alpha, 4, 5, or 6. So to calculate the normal mode resonances, we start with our interior models. We calculate a few derivatives and the Brunt-Väisälä frequency, and then we put them into a format that GYRE, the stellar oscillation code, can accept. GYRE tells us the frequency omega and the rotational splitting coefficient beta. We can then calculate the pattern frequency of each normal mode seen from inertial space. Resonance locations are found where m times the difference between the planet's rotation rate and the pattern frequency equals a positive or negative integer times the horizontal or vertical epicyclic frequency, depending on which type of resonance is sought of that radial location. These are 5 interior models for Uranus that we have successfully run in GYRE, our stellar oscillation code. 1 from Chris Mankiewicz, 3 from Ramona and Mankiewicz, and 1 from Scheibe et al., 2019. The Scheibe model is fully adiabatic and has a small core. The other models have no discrete jumps and actually no core. The Mankiewicz model has significantly higher internal temperatures. In reality, it's probably density and pressure that matter most for the planetary normal mode oscillations, but temperature may play some role. The models without discrete jumps are watery models, and each has a gradient in their water abundance. This gradient coincides with the stably stratified layer, shown with non-zero Brunt-Väisälä frequency. The Ramona and Mankiewicz models fit J2 exactly, and have J4 errors equal to -1, 0, and +1 times sigma J4. Here is the Neptune model we used, also without a core and with a non-zero Brunt-Väisälä frequency. Before I show you our results, I want to show the resonance location predictions from Mark Marley's unpublished 1988 poster, which highlighted the possibility of the L equals M equals 2 mode falling on the delta ring. But in other models he experiments with, the L equals M equals 2 mode can shift quite a bit. And it shifts inward a bit more with our models. Here are the predictions from one of our models, specifically the medium model from Aramona and Mankiewicz. The smaller M modes may fall entirely inside the rings, which could be why we haven't conclusively detected any of them with Voyager data. But several modes of oscillation order M between 9 and 14 may fall among the inner rings. If we run our other Uranus models, we get a variety of similar predictions. This gives us confidence to look among the inner rings and hope to find signatures of normal mode oscillations with M between, say, 7 and 14. One of the fundamental parameters we hope to constrain with ring seismology is the planet's bulk rotation rate. The Scheibe model uses the classical, or slow, rotation rate, corresponding to a period of 17.24 hours. If instead we use in our calculations the rotation rate provided in Heled et al. 2010, called the fast rotation rate, corresponding to a period of 16.58 hours, which would be inconsistent with the model, but can be done for exploratory purposes, all the resonance locations shift inward slightly. So you can see how Uranus's rotation rate is another parameter that ring seismology could help constrain. Running our Neptune model, we get predictions of normal mode resonance locations in the Gale ring, which is too tenuous to sustain a wave, but could still exhibit longitudinal structure. So what we are especially excited about is that planetary normal mode resonances likely fall among the inner rings of Uranus and in Neptune's Gale ring. To the extent that different interior models give us differences in where we can predict normal mode resonance locations, then once we identify the wave features in the rings that are caused by normal mode oscillations, we can eliminate a variety of interior models, and perhaps have evidence for or against a stably stratified layer or a diffuse core. So we look forward to the next ice giant mission to evaluate these predictions. The time from Marley and Porco's 1993 paper, predicting the locations of normal mode resonances in Saturn's rings, to confirmation by Cassini, was about 20 years. So it isn't crazy to start thinking now about ice giant ring seismology.